Converting the intense heat of combustion into the controlled movement of iron and steel was the primary challenge of the industrial era. On a microscopic level, that heat is purely chaotic. A gas trapped in a cylinder consists of billions of molecules ricocheting at high speeds, making it impossible to calculate the individual kinetic energy or trajectory of every single particle. Thermodynamics bypasses this complexity by shifting the frame of reference. Instead of tracking the swarm, engineers look at the aggregate behavior of the entire system. This macroscopic approach relies on statistical averages. We consolidate those billions of random collisions into three measurable properties: pressure, volume, and temperature. This abstraction is what allows us to treat thermal energy as a predictable engineering variable. To measure energy transfer, we first define a strict system boundary, like the metal walls of this pressure cooker, to isolate the contained gas. Properties like pressure and volume are point functions, meaning they describe the system's current condition regardless of its past history. The gas has no memory of how it reached its current state. These functions serve as coordinates. Plotting pressure against volume, a single point identifies the system's state at a specific moment. When heated or compressed, the gas moves to new coordinates. This transition between points is defined as a process. Mapping these processes onto a grid allows us to mathematically visualize invisible energy transformations. Historically, researchers mapped state transitions by isolating a single constraint to observe how remaining variables behaved. Robert Boyle's experiments focused on transitions where the temperature of the gas was held constant. Under this constraint, pressure and volume share an inverse relationship. Shrinking the volume raises pressure along a hyperbolic path. Holding pressure constant, an isobaric process, creates a perfectly horizontal path. These isolated observations unified into the characteristic gas equation, PV equals mRT. However, while this equation defines the relationship at any single point, it is difficult to apply to real-world engine cycles where pressure, volume, and temperature are all changing simultaneously. To calculate usable work, engineers must predict the exact geometric path the gas takes between its initial and final states. Every change in state requires an input of thermal energy. If the system volume is locked, the energy required to raise the temperature is called specific heat at constant volume, or CV. This contrasts with specific heat at constant pressure, or CP, where the gas is permitted to expand as it heats. CP requires more energy because the heat must increase the gas's temperature while simultaneously performing the mechanical labor of pushing a boundary outward. The ratio of these two heat requirements, CP divided by CV, is known as the adiabatic index, represented by the letter gamma. We use this index to describe adiabatic processes, transitions that occur so rapidly that no heat is transferred across the system boundaries. This ratio provides the mathematical framework for mapping cycles in high-speed, well-insulated engines. Thermodynamicists searched for a single mathematical model that could encompass all of these distinct behaviors. They found it in the polytropic framework. P times V to the power of n equals a constant. The polytropic index, the n exponent, determines the curvature of any state transition. Setting n to 0 removes the volume variable, leaving pressure constant and recovering our horizontal isobaric path. At n equals 1, we recover the isothermal curve of Boyle's law. Replacing n with the adiabatic index, roughly 1.4 for air, creates the steeper plunge of a zero heat transfer process. Representing a locked, constant volume system within this same equation requires another step. Isolating the volume by taking the nth root of the entire equation makes the pressure exponent 1 over n. Increasing n toward infinity shifts the relationship. The pressure term becomes 1, leaving a constant volume, which creates the vertical isochoric path. All four fundamental thermodynamic processes are now visualized as a single family of curves radiating from one common point. The polytropic equation consolidates a list of disjointed definitions into a continuous, interactive model. The ultimate utility of these geometric maps is the calculation of usable mechanical work. On a PV diagram, work manifests as a specific, measurable physical area. Because work is the integral of pressure over the change in volume, the area cast beneath a curve represents the energy exerted. Under a constant volume process, there's no expansion. The vertical line casts no shadow, representing zero work. Maximizing the volume expansion under the highest sustained pressure yields the largest geometric area, providing the most mechanical power. These theoretical paths dictate the physical design of engines like this locomotive. Real-world combustion cycles rarely achieve the ideal extremes of perfectly isothermal or adiabatic paths. Actual engine expansions follow a true polytropic path, falling into the mathematical gap between those ideal models. Engineers manipulate this path by adjusting cooling systems, cylinder materials, and piston speeds to shift the index value. By tuning the index, engineers expand the area under the curve, extracting more efficiency from the fuel. This process turns the unobservable chaos of microscopic particles into a predictable geometric map. By identifying that single index, thermodynamics translates the random thermal energy of the universe into calculated, predictable mechanical movement.